energy issues have become a more important aspect of swine production, and so many producers are starting to look more intently at their energy bills and figuring how they can conserve those dollars. And especially contract producers, it can be a significant amount of what their expenditures are. And so today we're going to try to cover some energy issues related to swine production there in Virginia. My name's Jay Harmon. I'm a professor and extension ag engineer at Iowa State, and hopefully this way of communicating will work pretty well. It's kind of new for me, and hopefully we'll be able to make it work pretty well. I wanted to give you a little bit of my background since I'm not there. I'm a professor in the ag and biosystems engineering department, and I've been here since '93. Before that, I worked at Clemson University and with extension there. And I'm a registered professional engineer. I teach, research, have a half-time extension appointment. I've done extension ventilation programs for quite a while. The current program that we're doing is we do half-day workshops, or really 6-hour workshops. And in the past 3 years, we've done 32 of those. We've had 600 attendants, and the people going through them have claimed that they finish about 40 million pigs per year. And so we've really done a lot of work with ventilation. Ventilation's one of those things that I think a lot of people don't have a lot of background in. They know pigs, they like to raise pigs, but a lot of times ventilation is something they just haven't had much exposure to prior to running a building. And I'm hokey. I got my PhD at Virginia Tech back in 1989, and so I was a little disappointed I couldn't work out a way to be there today, but I'm a Hokie anyway, so I guess I know where you live. So why is energy important? Well, these are some numbers. They come from University of Minnesota. It's a financial package that they use up there, and so these are Midwestern numbers. But what they found was wean to finish. You see the fuel and oil. That's the way they divided that up. It's only $1.22 per head. Utilities are 99 cents. Finishing, you can see similar numbers, a little less on fuel and oil versus utilities. And I think utilities includes phone and some other things as well. So it's not quite a nice, clean investigation of what the actual energy usage is. And then you see numbers for sow farms. So those numbers sound pretty small. So what's the big deal? Well, if you start to think about it in terms of what you can do something about, for instance, in a wean to finish, the energies or utilities is about $2.21 per pig. Well, that's only 2.3% of the total expenses, but it's 8% of the non-feed expenses. And so you get to thinking about it, and non-feed, well, feed is something you can't do a lot about. I mean, you need feed. You can't just say, well, I'm going to save money, I'm going to cut back how much I feed them. And so maybe we look at it from that aspect. That also maybe is a better situation for contract producers. You kind of see where that fits in with what you're paying for. And so, it's a significant amount, and it's something that you can do something about. And so, 8% for wean to finish. Sow farm is only 4.5% of the non-feed expenses, but it's still something that we can influence. It's money that we're losing out of our pocket. So let's take advantage of that and do the best we can to conserve it. So, like I said, it's something you can do something about, and many times there are energy savings things that we can do that don't really cost us anything. There's no investment, so that means the payback, rather than 2 years, is essentially instantaneous, and so they're more management related. So I'll try to cover several of those today. So if we look at annual benchmarks, if you're going to know when you're saving energy, you really need to know how much you're using. So if you're not currently tracking your energy usage, I'd urge you to do that. These are Iowa numbers, and so your numbers will be a little different because your climate's different than what we have here in Iowa. For sow farms, and some of these come from Missouri as well, but for sow farms, they were using 240 to 300 kilowatt hours per sow per year. LP, they were using 2 to 3 gallons per sow. Wean to finish, they vary a lot. If it's a tunnel building, 25 to 30 kilowatt hours per pig space per year, and that's per pig space rather than pig finished. For a tunnel versus a little lower for a curtain, you may be a little higher than that because your ventilation system operates at a higher level, probably more hours during the year. And then we're using, a good goal for Iowa has been 2 gallons of propane per pig space per year. Again, you might be closer to 1 or 3/4 of a gallon. And what I would urge is, if there's a group of you that you meet each other at the coffee shop once in a while, you kind of set your own benchmarks. Find out what's typical. Now, that's going to make a lot of difference with wean to finish, especially, are you the one loading your building in January, or are you loading in April or May? And so those values are going to differ. Like I said, benchmarks aren't really well documented, and so we're working to try to help that. But again, these are sort of Iowa numbers. So if you were asked to do an energy audit of your facilities, where would you start? Well, with electricity, you think about lights, you think about fans, heat lamps. What about some other hidden uses? With propane, you think about heaters. What about insulation or just management of the ventilation system? And so all these things are things we can think about, but where do we start? Well, I'm going to try to touch on most of these today, and so we can kind of get a feel for what kind of magnitude they have and how important are they. So let's start with insulation. Many people in their homes, if you have an energy audit in your home, a lot of times they'll focus on how much insulation do you have in your attic, and is that appropriate for livestock? Well, most of the time, in fact, we lose 80 to 90% of our energy through ventilation. In your home, you're not really ventilating, and so insulation really helps reduce the total heat loss. So we have to remember, with our livestock building, we're ventilating, we're losing a lot of heat through ventilation, and insulation only treats the wall portion of that. So we're really only treating that 10 to 20, maybe 30% of our heat loss, and so it's not quite as clear cut. And so what I've done, I've used weather data from Richmond, Virginia. They have weather data that tells me how many hours is typical between 5-degree increments. For instance, like between 85 and 90 degrees, how many hours per year is it typical that the temperature's within that range? And then I go through this exercise where I try to find kind of an average usage, and I end up using 5-pound pigs at 3 cubic feet per minute ventilation rate. So I go through this to find out kind of how much insulation would we really need, or what would the payback be if we made some changes. Okay, and I used $1.75 a gallon per LP. I'm not sure what it is right now, but at the time that I put this together, that was pretty close. So here's, in this chart, what I did was, I said in the left-hand column here, you see it says current insulation depth. So if you think about your attic in your barn, how deep is the insulation? Is it only 2 inches, or do you have 6 or 8 inches? Okay, so that's what this column represents. The center column then is if we decided to add 6 inches of insulation, so we blew in 6 more inches of insulation, what would be the savings per year? Okay, and you can see that if we only started with 2 inches, we add 6 inches, so now we have 8 inches. There's a pretty good savings. However, the better insulated you are, the less the payback is. Okay, so it's sort of a diminishing return. And you can see here's the payback. This is based on some numbers I had for what it costs to blow in insulation. Maybe off a little bit, but you can at least kind of see what the magnitude change is. And so what you see is that if you only have 2 inches to start with, within a year you can pay it back just with LP savings. But if you get 4 inches, well, it's going to take you 3 years, and so forth. And so if your existing building you have less than 4 inches, maybe it's justified to put more insulation in. It would help building longevity and so forth. But insulation is not usually the first place we start with our concern, just like it would be with a house. And so I wanted to contrast that a little bit, because a lot of people, when they think energy savings, insulation is one of the places they jump to. This is perimeter insulation, and by perimeter I mean around the outside edge, lower edge of your building, the concrete foundation. Most of the time that's not insulated. Partly it's hard to maintain. Some of the farmers I've worked with have gone in and dug around their building, or they put it in at the beginning. They put insulation there trying to reduce their heat loss. And so again, you see that if there's none to start with in this far left column, then if you add 1 inch, what's the savings? And so you can see, even if you have none and add 1 inch, it's still 2.5 years. That's probably not a very good payback. If you have 1 inch, you're only going to save about $40 per year. If you add another inch, that'd be 24 year payback. So that wouldn't be very good at all. And so if there's no insulation, maybe you can justify it. It wouldn't be the place I would start, but there's some considerations from condensation and animal comfort, perhaps. Now again, because you're in a climate that's not quite as harsh a winter as what we have, I think that makes it even less of an opportunity than it might be for some other places. And so here I just wanted to illustrate this a little bit. Here's an uninsulated concrete wall. If it's 70 inside and 20 degrees outside, what's the situation? So 6 inches of concrete has an R of 1.33. So that's about what a pane of glass would be. Maybe a little better than a pane of glass, but not much better. And so you have heat flowing from hot to cold, and the inside surface is about 44 degrees. So that means anytime in this situation, anytime your environment inside the room is above, or the humidity is above 39% relative humidity, which in a livestock building is most of the time, you're going to get condensation. So the wintertime, when it's cold, 20 degrees, you're going to have condensation around that lower part. If we went in and put 1 inch of insulation around it, so now that R of 1.33 becomes 6.33. Insulation, I show pink board here, it can be blue board or whatever color you can come up with. A lot of those are about an R of 5 per inch, and it changes that inside surface temperature to 65. Now condensation doesn't happen until 84% relative humidity. So you can see there might be some pig comfort issues, there might be some condensation issues, that you could save, but from a purely an energy saving standpoint, probably not the place to start either. Okay? This, I just wanted to show you this as well. This is some older data, but this is how being exposed to a cold wall affects pig comfort. Okay, and so you see on the left column air to wall gradient. So in other words, if the wall, or if the air was 70 degrees and the wall was 23 degrees below that, so that'd be 47. So that's about what we came up with, was about in that neighborhood. Then it would make the pigs feel 13 degrees colder than that actual temperature. Okay? So that's like you standing in front of a picture window in the wintertime. That window's cold. You're gonna, even though your house is 70 degrees, you could feel like it was maybe only 57. Okay, 13 degrees colder. It's how effective temperature is the temperature you feel like it is. Okay, and so that's the influence those cold surfaces can have. All right. So let's move on to some other things that might be a little more beneficial than insulation. Okay. First of all, let's talk about lighting. And I know one of the speakers on the program is going to talk about lighting and LEDs, and so I don't want to go too deep into that. I believe that person is much better versed at lighting than I would be, and so hopefully he'll have a good picture for you. But I just wanted to give you some background to think about with lighting. Lumens is the quantity of light output. Most of the time that's labeled on the package itself. And then there's an average rated life, number of hours for half of the bulbs to burn out in the laboratory. So they go put these in a lab, and when half of them have burned out, that's the life they set up. And then the efficiency is that lumens divided by the number of watts. Okay, and so in this case that'd be 60. So that's a way to kind of compare light, so you're comparing like things. So this is sort of an overall chart. I'm not going to really go through this, but it is available at our Farm Energy website, and I'll give you that at the end. There's a lighting fact sheet that lists these, and we have incandescents here, although some of these incandescents they're phasing out, and so they'll be harder and harder to find in the future. Compact fluorescents, cold cathode compact fluorescents, LEDs, and LEDs are advancing so quickly that this is likely a little out of date. And then there's different fluorescent lighting. So I just show these as a comparison, and you can see the lumens per watt. Some of these are up in the 100 range, like LEDs and some of the T5 fluorescents, while incandescents, were in the 10 to 35 range for most of them. Okay? So those are sort of your options. Well, in a lot of times in the past, we've looked at incandescence versus compact fluorescence. It's an easy change. You screw in a different light for the most part. And this was sort of the step that many people made a few years ago. LEDs have changed this perspective quite a bit, and like I said, the other speaker will be able to handle this much better than I am. But I wanted to just give you an example here, and so you can see that the incandescent, I picked a long life bulb of 75 watts versus a 20 watt compact fluorescent. You can see lumens are sort of similar. The rated life of this bulb was 1,500 hours versus 12,000 for the compact fluorescent. Now I have assumed, and I used half of those lighting. One of the issues with lighting changes is that many of the bulbs have a shorter life when they're in a globe. You have conduit and a light globe, to protect the bulb. And because the heat builds up in there, many times it shortens the life of that bulb. And so I think probably a good rule of thumb might be to say they'll really not make that rated life. Maybe they'll make half that life. I found at the time that I put this together, I found 84 cents for a normal long life bulb versus about $1.80 for a compact fluorescent. So about twice the price. If we said they were operating 8 hours per day, that would be 2,920 hours per year. So again, how much of an issue is it? Depends on how long you're using them. You know, if you were only using lights a couple hours a day, it's probably not going to be quite as big a deal. And so you can see here, this would be for the incandescent bulbs, that would be 219 kilowatt hours per year, or $21.90. If the light, we'd actually need 3.89 bulbs to make to be able to operate throughout a year, because we have 2,920 hours divided by 750 hours of life, so that's $3.27, and then our total cost would be $25.17 for that one light fixture. If we compare that then in this case to compact fluorescents, we have 58 watts per hour. You know, it's about a fourth the size, and because it has a longer life, we only need really a half a bulb a year, so a bulb would last about 2 years, and so the total cost would be $6.67 per year, and so the savings per bulb would be $18.50. Okay, makes sense. So if this is the situation, and we could do the same thing with LEDs, you'd have to look at initial costs. They're a little higher initial costs, but the energy savings would be greater. But you know, this is a very quick payback, and so if you're still using incandescents, it's definitely something worth looking at, some options. And so just as a magnitude of savings, for a 900 head gestation barn, for instance, if we had 150 bulbs in it and that were on 8 hours a day, a 75 watt incandescent bulb would use almost 33,000 kilowatt hours per year, where 20 watt bulbs would use you know, about a fourth of that. And so there's a potential energy savings at $2,400. Now, this is going by the lighting recommendation that Midwest Plan Service has for gestation barns. It's probably more bulbs than most people use, and it's probably more hours than some people use. But if you were breeding in that barn, you very well could have the lights on 8 hours a day. So I think some of these things that we don't think about, lighting, we don't really think about it being a very big magnitude. But in a large barn, it certainly can be. Ventilation. Let's spend some time on that. That's really my bread and butter. I spend most of my time in extension working with ventilation. And it's far and away the biggest potential for wasted energy. Okay, like I said before, 80 to 90% of the heating energy is lost through ventilation, and controller settings and fan selection have a big influence on energy, not only propane but electricity as well. And so the next portion of this talk I'm going to spend on going through some of the ventilation issues. So what about the proper ventilation rate? Well, again, I'm using the same kind of model that I developed. I've compared it with some actual data, and it doesn't do too bad a job, so we can kind of play what if with it. And so let's use a 1,000 head barn, 41 by 200 roughly, and if I model 50-pound pigs at 3 CFM per pig, and with a set point of 68 degrees, that gives me kind of a general average. Now, the one thing that you have to realize about this is it does make a difference whether you're loading pigs in January or April. And so if you had a big system and you were loading one group of pigs every week into a nursery somewhere or into a finisher somewhere, then these average numbers might come out. But if you're loading pigs in in January and somebody else is loading them in May, you're going to get a lot different numbers. So this is just kind of a baseline way to compare it. Our minimum fans, we'll say, are 24-inch fans rated at about 7,000 CFM. So how much does it cost to overventilate? You know, many times people overventilate and we don't even realize it. Well, if that one fan is set at 50%, and by 50% I mean it's actually moving 50% of what its rating is, then we're going to use about 170 gallons of LP per 1,000 pigs. So that far blue bar, this is sort of what our goal would be. So it's really not that much for your systems in comparison to ours. We're using almost 2 gallons per head. And in this case, this would be closer to about 0.2 gallons, about a quarter. If just a 5% difference, so this is a 10% overventilating, now we go from about 170 up to about 210 gallons. You know, still not a lot, but you know, it's quite the difference. We look at a 20% overventilating, which would be the equivalent of 60% of this 24-inch fan rather than 50%. Now we're at about 350. So we've almost doubled our energy usage, our propane usage, with a 10% change in the setting on our fan. And you can see this continues up. Some people, some of our farmers tend to use two 24-inch fans on 40%. For some reason, that tends to be just kind of the one they use. And you can see in this case, that's 60% overventilation. About 950 gallons of LP per 1,000 pigs. So that's almost 1 gallon per pig per year, per pig space per year, when less than 0.2 would have done it. And so, you know, that can make quite a bit. So we really have to work on fine-tuning our ventilation. We want to ventilate enough to keep good air quality, but not so much that we're wasting energy. Okay? Variable speed fans make it difficult because we don't really know how much they're moving. Okay? The poultry industry, most of the time, they use large fans. But their buildings are so large that they can just bring them on one at a time, and they don't fool with variable speed in most cases. And so why do we use them? Well, here's an example. You know, if you have a 24 crate farrowing house, minimum ventilation is 20 CFM per crate, so that's 480 CFM. The smallest fan that's available is 1,000 CFM. So we use variable speed to cut that in half, essentially, to provide that minimum ventilation. 1,000 head wean to finish barn, usually you start off pigs about 2 CFM per head, and so that's 2,000 CFM. A 24-inch fan is 6,000 CFM. Well, in this case, a 24-inch fan really can't slow down to do 2,000 CFM. Many times people oversize those minimum fans, and so really for a 1,000 head barn, we'd be better off using maybe 18-inch fans or something smaller. Normally, a good rule of thumb is, for instance, in this case, if we need 2,000 CFM, we wouldn't want a fan that was more than twice that size. Okay, so in other words, a 4,000 CFM fan can be slowed down enough to provide 2,000 CFM, but a 6,000 CFM fan really can't be slowed down enough to get to that 2,000. Okay? And so many times fans are oversized. But the point being, we need variable speed to be able to get there. Okay? This is another tricky aspect is here you have the voltages on a specific fan, and you can see this top red line is full voltage. And so at a static pressure of zero point 0.1, we're delivering about 7,000 CFM. At half voltage, so 120 volts, we're only delivering about 800 or 900 CFM. Okay, and most of the time, if you put that in place and tried to run it that way, the wind would blow against it, and it would not be a good situation. You couldn't count on that ventilation, and so this isn't kind of a linear system. And so really the only way to do this is to try to start off the ventilation system by setting it. Let's say you had a 18-inch fan that did move the 4,000 CFM we were talking about. Start it off at 50%. See how the air quality is. Adjust it based on air quality. If the air quality is not good enough, tweak it up. Maybe change the setting to 55%. If it's still pretty good, and you think maybe you're using a little extra propane, you need to tweak it down a little bit. And so it's a little bit of an art. The other way that some people do this is they use an anemometer with the fan, and I don't have a picture of this. I was going to put one in, and I couldn't locate one. But another way people do this is if they know what the full speed rating is of a fan, they'll use an anemometer in front of the fan, and then that gives you the velocity. So that's 100% velocity. So if you need 50% of the total delivery, so we're going from 4,000 to 2,000, let's say, then that means you'd need half that velocity. Okay? So you could use an anemometer in front of the fan, measure the air speed going into the fan, the exhaust fan, change your fan setting until you got to half the speed it was at full speed, and that would say that fan you started off at 4,000 CFM, now you're at about 2,000 CFM. Okay, and that's if you have questions about that, I can try to provide you with a little further information on that, but because that's probably not as clear as it should be. Here's some example data from a fan, and so this comes from Best's lab. It's a testing lab at the University of Illinois. It's online. You can look up all kind of fans on here, and I'd really urge you to do that if you want to know more about different types of fans. And so you can see the static pressure here on the left. Normally we operate static pressure between 0.05 and 0.1. This is the RPM, and you see they're all the same here pretty much. So it's a constant speed fan. And then CFM. And so as there's more resistance, as the static pressure grows, the amount of air that a fan will move drops off drastically. Okay, so we're operating in this range most of the time. And so if I was picking a fan, I'd say this fan, I could count on it moving 5,740 CFM. And then this last column is the efficiency, CFM per watts. And so that's a way you can compare from an energy standpoint is, how's this fan compare energy usage-wise to other fans? In fact, the lab was started as part of an energy program years ago just to do that evaluation on fans. So how good should a fan be? Well, what I did was I went into Best. This has been a couple years ago, but I went into Best and I looked at all their fans based on diameter. And so you can see the diameters here on the left. And then I took the median rating. And so in other words, half the fans that are less than 16 inches, half the fans have efficiency ratings below 7.9. and half are above 7.9. Okay? And so what I thought was, well, if I was picking a very efficient fan, I wanted to pick one that I said was an efficient fan. I'd probably want to be in the top quarter of the ratings. And so that's what this column is. Okay? So that means if I was trying to do that for a given fan size, I'd want to be at least at this rating. And you can see as fans get larger, they get more efficient. All right, so they don't. Some of them are belt driven and so forth, and so the efficiency goes up as the fan goes up. So to say, well, I want everything above 20, well, it'd be pretty difficult to get a small fan that had a rating of 20 CFM per watt. So you'd want to have a little kind of a moving scale depending on the fan size that you were talking about. And so this might be a decent way to approach that. If we want to just compare, this is, I set this up for a tunnel building, wing to finish, and so they have a lot of tunnel fans. 120 CFM per head is the top end where you'd probably be. And so I set it up with two fans that were about 4,000 CFM each, one fan at 6,000 to 7,000, one fan at 10,000, and then four other fans. And so if I pick the most efficient fans and for a system, I'd spend roughly $1,300 if the price of electricity was 10 cents per kilowatt hour. About $1,300. If I chose the least efficient ones, I'd spend about $2,300. And so each year I could save $1,000 just by picking the most efficient fans in this case. Okay, again, that's kind of annualized. It depends on when you would load the pigs, but you could save more than that in some cases, less than that in some others. Also, fan maintenance is very important. A fan that's dirty will usually move about can move as much as 40% less. You know, the shutters get kind of clogged. They don't open as far as they should. Fans get dirty. There's just junk in them. And so cleaning fans, maintaining fans is very important, because when a fan moves less than it should, then it'll trigger the next stage of fan to turn on more quickly. What about proper temperature? How can you tell if you're at the proper temperature, and how much does using an improper temperature cost? So here what we have, again, this is a 1,000 head curtain-sided building, 50-pound pigs there in Virginia, and you can see that at 68 degrees, this is what I'm considering the baseline, we'd use about $260 worth. If we kept it 5 degrees warmer than we really need to, that would actually increase our energy usage, our LP usage, by 310%. Turning it down less than we need to, we can save half if we do it 2 degrees. But again, there's other costs to that. The pigs might not perform as well, and so forth. But many times I'm in buildings where the temperature is too warm rather than not warm enough, and so paying close attention to this is important. Watching their behavior is one of the biggest keys, and so you can see this from an experiment we did quite a few years ago, where we had pigs at different temperatures. I don't remember what the temperatures were right off, but you can see that these pigs huddled because they were cold. These pigs kind of laid out. They're touching each other. Pigs are pretty social animals, so they'll tend to touch each other when they're comfortable. And then these pigs, were probably too warm. They didn't really touch each other very much because of the way they lay. Now, the other conclusion you could draw is that white pigs are less friendly than black pigs, I guess. But that's just the way that the trial went. But watching your pigs, observing how your pigs move and lay. So if you can sneak into the room without disturbing them, or look through a window, you can tell a lot about pig comfort just by watching how they lay. Properly setting the heater and fan controls, though, can make a big difference as well. And so let's talk about that for a minute. So here, what we have, this is the way that a normal fan control works. Normally at the set point, the first fan, the minimum speed fan, variable speed fan, will start to increase speed, and above the set point. And so we may be operating at some minimum percent, 50%, let's say, and it ramps up to 100% over some bandwidths, 2 degrees perhaps, okay? And so that's the way the fan operates. So that's considered cooling. The set point isn't the average room temperature, it's kind of the trigger point for when cooling begins. Now for heater control, the way it works is below the set point. And so as the temperature drops below the set point, in this case I'm showing the set point is 68 degrees, it gets to some point and the heater comes on. It heats some amount. Some controllers call it a differential. Some controllers you just put in the heater off temperature, and so it'll heat perhaps 1 degree. And what happens is that once the heater shuts off, sometimes that room will continue to get warmer. So the sensors can respond more slowly, or sometimes you have a big heater in a small room. It just takes time for the heat to get spread around. So once you turn the heat off, it'll continue to go up a little bit. There's a heater offset programmed into these as well. And so in this case I'm showing 1.5 degrees below the set point is where the heater is shut off. Okay? So you can see kind of the way the system works. The temperature drops to this point, which is 2.5 degrees below the set point. The heater comes on, heats it back up to 1 degree, and then shuts off. Okay, so in the winter time, if you're in a heating mode, most of the time it should be below the set point. Okay, so what can happen is if this is too small, this set point is, let's say, 0.5 degree, perhaps you can overshoot it. And so what happens then is that you overshoot the set point, so the heater runs, it shuts off, and then you hear the fans start to ramp up, start to increase speed. And so that's one thing I listen for in a building, is that if I go in, I hear the heater run and then shut off, and then I hear the fans start to ramp up, that means they're fighting each other. And so we're putting this heat in the building, and then right away the fans turn on to exhaust it. And so that means this offset is too small. We're turning the heaters off too close to the set point. And so here's some a case study example from a farm. Actually, this is in southern Minnesota. And so you can see the green line is the furnace run time. And so during certain hours of the day, you can see some hours it runs 8, 7, 7 to 9 minutes. Then it dropped here a little bit, but it was running some during each hour. They changed the set point at this point. So in this case, the heater was coming on 2 degrees below the set point and turning off 1 degree below. Then they changed it to 2 degrees below the set point. It would turn on and turn off 1.5 degrees below. So in other words, it only heated the room 0.5 degree and then turned off. It's only a 0.5 degree difference. And then suddenly the fan stopped running, or the heater stopped running. Just that 0.5 degree. And so what was happening was the furnace and the fans were cycling back and forth. They saved 3 3/4 gallons of propane in one day just by changing that 0.5 degree. Okay, again, they're in a colder climate, but you certainly can save propane just by making sure that fighting between the heater and the fan doesn't occur. There's a fact sheet on this as well on our website that may be of interest to you. Initially, I recommend they set offset. That's how many degrees below the set point the heater turns off, so that's the way you can remember that. It's 1.5 to 2 degrees, and then the offset needs to be larger in rooms where the furnace is large for the room size. But the most important thing is to listen to see, does the furnace run, and then do the fans increase. Those should never be occurring in close proximity. It could be you'll hear the furnace cycle in the morning, and then maybe at noon it quits running and doesn't cycle, and then maybe in the afternoon it gets warm enough that the heaters start to increase speed and start to ventilate a little more. But you should never have the heater run and then the fans increase in proximity to each other. Zone heating is another way that people approach that. And you can see the radiant heaters here, the brooders. And the idea is sort of like that. We talked earlier about how the cold picture window makes you feel cooler. Being exposed to a hot surface makes you feel warmer. So if you've ever been in a building in the summertime with no, like in a shed with steel roof on it with no ceiling in it, you feel hot because that roof is hot. Well, this radiant heater works much the same. There's a hot surface there, so the pigs feel warmer even though the room temperature is cold. And so what we do is we're able to keep the room temperature cooler, use less heat that way, and just provide kind of a zone where they're more comfortable. And so we're trying to take advantage of that. So the benefit comes in lowering the room temperature. That's what we're trying to do. We're trying to save energy, propane. And so without lowering the room temperature, it's kind of pointless. Okay? So let's look at this a little bit. The controller settings on this can be very important. And so here I show that a brooder set point might be 82 degrees. And in many cases, they have many people set the room set point at 68. So they say, well, I want to keep my room colder, so I'm going to set my set point at 68 degrees. And these are heater settings down here then, okay? Space heaters. Well, what happens is that if you have kind of a warm day, your heaters, even when they're on low or just on idle, are producing some heat. So sometimes the room temperature begins to rise, in this case above 68 degrees. Well, if energy was free, we'd probably just maintain the room at 82. Okay? But we're trying to save energy. By setting the room set point at 68, our ventilation starts to increase above that 68. So what that means is, even if the room starts to get a little warmer just because the day is warmer, we're exhausting that heat. So it acts like 68 is really where we want it. Well, that's not really the case, and it's sort of wasting some energy. And so there's a better way to set a system if you're using brooders. So if you're using brooders, the better way to do it is to go ahead and set your room set point maybe even a little above the brooder set point. We don't really need ventilation, extra ventilation. We need our minimum ventilation all the time. But we don't need extra ventilation until the room gets hot, right? Extra ventilation is to get rid of heat. And so we set our room set point a little higher than that, but we still have our heaters come on down here. Okay? So, in this case, what happens is the room will actually operate down here in this cooler zone unless there is extra heat. And then maybe it'll start to float up a little higher. But we don't start ventilating extra until we get above the set point, above the brooder set point. All right. Again, that's one of those points that might not be real clear, especially if you're not operating your controller. If you're not the one operating it, it's probably not as clear to you. But there's no reason to ventilate to try to maintain a cold temperature if in an ideal world we'd really have a warm temperature anyway. So what this does is it really delays the extra ventilation that we're bringing in until we really need to get rid of heat. Okay? but we don't turn on the space heaters until some cooler temperature. All right, again, that's one of those fuzzy things. I'd rather be there because I could tell by the look on your face whether it's look on your faces by whether it's soaking in or not, or if you have questions. But hopefully we can answer those via phone. This is just some brief data. Also, heat lamps in a farrowing barn. Dr. Shin in my department did this work quite a few years ago now, but he was comparing 175 watt to 250 watt bulbs. He had more pigs actually by using the small bulbs, plus he had reduced energy. And you might say, well, why did he get more pigs with smaller bulbs? Well, if we think about it, here's some pictures of how they lay. And so with the 250 watt at 7 days, you see there's a place there where they're laying away from it. Here at 250 watt with 14 days, they're really laying away from it. So that means it's too hot right underneath, right? They kind of form a donut around that. Well, if they won't lay right under the lamp, where do they end up laying? They get up underneath the sow, right? So they were losing more pigs because it was too hot under the heat lamp. So this lower wattage, they're filling in the space pretty well, and they didn't lose as many pigs. And so that's the amazing thing to me, is even something as minor as the height or wattage of a heat lamp can make a difference on pig performance. How many pigs you wean, so maybe we should call that a game of inches, where it's just even something so slight as that can salvage more pigs. That always just fascinates me, that something so insignificant can do it. This is another way some producers have done that. They also change the wattage that the voltage that those bulbs receive, and so they can turn down the temperature to try to maintain it. Now, some people will try to do that with rheostats, but they chop the voltage and they don't really save any energy. Now, that doesn't mean that you're not providing a better environment for the pigs, but it doesn't really save the energy that you would with some kind of variable frequency controller. Just a couple other management things to think about. If you have curtains, they should overlap at least 3 inches. That helps with leakage and helps ventilate better, keeps the cold air out, and can change how much heat you're using based on that. Sometimes if you have pumps, sometimes there's pumps you're not thinking about. Could they be converted to 3-phase? Do the lines need to be clean? Those can use a fair amount of energy at times as well. And then there's also emergency thermostat backups. Many times they're in buildings, and if they're not set properly, sometimes they can be turning on fans or heaters when we don't really want them to be on, and so it's important to keep up with them. Just a summary, few points here. Begin by tracking your energy usage. Ventilation management is critical to energy management. Controller settings are very important. Proper temperature is important. Insulation may be helpful, but many cases it's not, and then lighting can actually pay back as well. So with that, I'll try to answer questions for you via phone, and I hope that you received a few good points out of this.